Hello, so today we are going to do this problem which is part of Leetcode daily challenge, greatest common divisor traversal. So basically this problem, we have an array and we have a rule where we can traverse between two positions only if the GCD of the values is bigger than 1. So only if the greatest common divider between the two is bigger than 1. Okay, so basically what this means is that they share a factor. There is a factor of this one and this one, and your task is to determine that for every pair of indices in the array, so all the pairs of indices where one of them is smaller than the other, there exists a way to traverse between them that can take you from I to G, with the constraint that you can only traverse between two positions if you have this condition. Okay, and the goal is to return true if it's possible to traverse between all pairs, and false if not. So for example, if we take this first example here, 2, 3, 6, the pairs we have are 0 to 1, 0 to 2, and then 1 to 2, right? Those are the only pairs of indices we possibly have. And so we check first between 0 and 1. We can first go from 0 to 2 because the GCD of 2 and 6 is 2, which is bigger than 1, because 2 divides 6 and 2 itself is a prime number, but the 2 share a divider, and that's their greatest common divisor is 2. So we can move from 1 to 2. So we first do it like this, and then from 2 to 0, 2 to 1, we can also move from 6 to 3 because the greatest common divisor between 6 and 3 is 3, which is bigger than 1. Okay, and then if we try the rest, which is from 0 to 2, well, we already said the GCD there is 2, so it's bigger than 1. And from 1 to 2, we already said the GCD is 3. So for all of them, it is possible, so return true. So that's the core idea. But if you look at the constraint, the array length can be up to 10 to the power of 5. And the numbers themselves up to 10 to the power of 5. So this already eliminates any open squared solution. And so this tells you that you can't really go through, basically do a loop for indices and do a loop for the other ones and then check the GCD for both. You can't do that. So we have to find another way. So let's see how we can tackle it. Okay, so let's think about how we can tackle it. Well, if we just ignore the constraint where it's 10 to the power of 5, then the easiest way to do it is to just create a graph, right? Where basically the nodes are the indices of the element. And then the two nodes, I and j, we put an edge between them only if the GCD of the element at position I and the element at position j is bigger than 1, right? That's literally the definition of the problem. And then what we do is we can check if there is more than one component. Why? Because if there is more than one component, one connected component, that is, if there is more than one connected component, what does that mean? That means you have something like this. You have some nodes that are connected, and then you have either one node that is not connected, or maybe you have some other structure where you have two nodes, or maybe some other nodes, and then some other nodes here in another different components. You might have more, but let's just stick to just more than one, whatever the number is. Then what does that mean? That means you can traverse between the nodes here, but you can't go from one of the nodes here to one of the nodes here. And the nodes here are all the indices of the array. And so the problem actually, if that's the case, then we should return false, because the problem asks us if all the nodes you can traverse from one to the other. If we can't, that means we return false. And so when do we return true? We return true if there is only one component, because if there is only one component, that means all the indices are connected, which means we can go from any index to any other index. Okay, so our first observation, let's write it down. So our first observation is that if there is more, so basically if number of connected component is equal to 1, that means we can traverse from any index to any other index. So in that case, we return true. Otherwise, we return false. If it's more than 1, which is basically more than 1, we return false. Okay, so now how do we do this? If we do it in the graph way, where we just go through every pair of indices and check if there is the GCD is bigger than 1, then we make the nodes neighbors, and then we can do whatever approach to find the number of connected components. Then creating the graph alone is going to be O of n squared, but we don't want that. Okay, so we need to find a better way. So our goal is to find a better way to construct the graph so we can find the connected components. Because finding the connected components is this here, finding the number of connected components. You can do it in O of n using either, you could use DFS or you could use union find. Okay? And so our problem is constructing the graph. So how do we solve that? Well, let's go back a little bit to the definition of a GCD of two numbers. Let's actually just do A and B. What does it mean that this is bigger than 1? Okay? Basically, all this means is that there is some number. That number can be A, can be B, or can be another number that divides both. That number can be one thing to remember, but there is a number that can divide both. So what does that mean? At least one number that divides both, right? It can be more, and so we pick the greatest common one, but we have, this means basically at least one number that divides both. Divides A and B, okay? And that number needs to be bigger than 1, okay? So that's the first thing to think about. Now, what does mean that a number divides A and B? Well, basically it means that it's a factor, okay? And if you think about that factor, if that factor is not a prime, then you can actually divide this factor into multiples of prime. And so all we need to find is the prime factor that they share together. So if we can still think about, let's think still about doing it O of n squared by using this prime factor approach. How can we do that? Well, we can just go through all the indices first in the range of the length of A, then go for G in basically from I plus 1 to the length of A, but then calculate the prime factors of A of I, and calculate the prime factors of A of J, and find the common one, if they share a common one. So basically we get the prime factors of I and prime factors of position J, and do the intersection. Okay, now if the intersection is bigger than 0, the length basically, then that means there is a greatest common divisor that is bigger than 1, because they share a factor, right? And so if this is the case, then we can immediately create an edge between I and J. Okay, so now, knowing that, this is still O of n squared though, how do we reduce that O of n squared? That's the key thing we are looking for doing here. Well, we have to think about what if we connect only what if we connect the prime factors themselves of a number? What do we mean by that? So let's say, for example, I have 6 and the factors are 2 and 3. So let me just connect 2 and 3. And let's say, for example, the other numbers we may have are, let's see, 1 second here. Let me just pick up a couple of examples that will be useful. Let's say, for example, maybe 2 itself. So we have 2 as a prime factor. And let's say maybe we have 8 where we have 2. And let's say 9 where we have 3. So with this, what we can do? So first we do the prime factors of 2, then we have 2 already connected. then we have 2, then we have 3 already there. Let's maybe take another one. What is, let's say, of, let's say 15, for example. So the prime factors of 15 are 3 and 5. So we have 5, we connect those together. Okay? So if we have an array with 2, 6, 8, 9, 15, should we return true or false? Now we constructed the graph like this, and we have one connected component. What does that mean? Well, this means basically that that all of these factors share each number share a factor between one of these. Okay, because otherwise, let's say for example, if we had a number that doesn't share a factor with these, so maybe let's say we have I don't know, maybe 11, right? Let's say we have 11, okay? So 11, the only prime factor is 11 itself. So we'd have 11 here, not connected to anything. So immediately here, we have 2 connected components and we can return false. So the core idea here is, let's not actually build a graph of the indices. Let's build a graph of the prime factors of the elements. And we only need to connect when we build a prime factor. Let's say maybe something has a long list of prime factors, let's say P1, P2, P3, P4. While we are generating these prime factors, we can just connect each one with the next one. We don't need to connect all of them together. We don't need to do P1 like this, because already we can reach P1, because already we can reach P1 from going to P2, then P3, P4. So we need to only connect each one to the previous one. So that's the core idea here is, let's not do a graph of the indices, do graph of the prime factors of each one. And if there is a one that doesn't have a common factor with any other number, then its factors will be in a different component. Okay? And so now what we can do is just calculate the prime factor of each number, connect the prime factors of that number together, and then check if that will give us the union, if that will give us more than one connected component. Now, how do we calculate the more than one connected component? We can use union find. And what's good about union find is we can just actually construct it while we are traversing the numbers to create the prime factors, right? Because as soon as we find 2 connected, we create a connected so basically, for example, if we find first, we get 6, 2, and 3. So we create the edge, but we also create a component saying, with union find, saying this is the root of 2 was 2 before, the root of 3 was 3, which once we connect them, we say that we give them a common root. So here, let's say 2. Then we do 5, okay? So 5 first had just 5, and so we connected it together, okay? One thing to note here is that here we actually don't connect the nodes themselves. We don't need to actually have them be the factors. We can have them be just the indices. So what I mean by that is we have here the index of this element. So this is 0, 1, 2, 3, 4. So for 6, this would be 1 and 1 here. So it's just 1, the same node. For 2, this would be index 0. And then for 5, which is connected to 3, which is for 1, this would be index 4, for example, okay? So basically for each factor, we actually connect the indices of the element. So for example, this one here, we can do, it's actually, let's say if 11 is here, index 5, this actually would be 5. But still the same idea. We will just put the indices there. But still the same idea, calculate the prime factors, connect if they share a prime factor, and then use union find to find the number of components. I hope this idea was clear. Now we can just code it up and make sure it passes. Okay, so let's write the implementation here. So the first thing we need to do is let's just go through the numbers, right? So let's go the numbers and the indices, so enumerate them. And then here I will just name this A. And we will calculate the prime factor for A, right? So we'll write the definition of prime factors later, but for now, let's just say it's just pass, okay? Just assume it will give us a list of the factors. So we can go through the factors, and remember we want to connect the numbers that share a factors. So we should say prime group of, basically we can just have it as a map here with a list like this. And we say primes group of F, we append the index, okay? So basically all numbers that have the same share a prime factor will be in the same group here. But now we will need to connect them. So basically connect basically I with the previous index added in, okay? So let's say this was, the factor here was 2. So, and this index is 3. So we want to connect, and the previous index, let's say, is 1. The previous element that has a factor of 2. Then we will want to connect this index 3 with index 1. Because they should be in the same component because they share a factor. So how do we do that? Well, first we want the primes group to be, if it's bigger than 1, because there is no previous if it's not bigger than 1. But also remember, we are going to use union find to connect the components. And so let's say union find like this, we'll define it later. But here we want to connect in the same component, so that's what you use union for, this index I and the previous one. The previous one is the one at index -2, because at index -1 in Python we have I. So you could also use something like, if this makes it more clear, yeah. So with index I with the one before it. We'll define the union find in a moment, but this is the core idea here. So let's just define our class union find. It will take n, but we will need to define 2 functions. Find the init function, which gets passed the number of element, and this one here needs to have just an element, and then we need to find the union of 2 elements, which is going to be of A and B. This is going to be the union. We'll do all of these in a moment, but for now let's just do pass like this. Okay, so now what do we do? Now we need to find if we have the number of connected components. Okay, so how do we do that? Well, we can now we know we return true only if all the numbers are connected, if all the indices are connected. So let's find just the index of the root basically of 0, of index 0. How do we do that? Well, we can just use our union find and say find the root for index 0. Because remember, our union find is constructed of the elements, the nodes are the indices of the array. And then we can go through the other, so if number of connected components is bigger than 1. If it is, then we're going to return false. So we can just go through the other elements and see if any of them has a different root than the root of the first one, then that means we have more than one connected component, right? And so we can find the root of I. So here, root of 0, this root of I, we can just find root of I. Now, if root of 0 is different than root of I, then that means we have more than one connected component. So in that case, we can return false. So that means we can return false in this case. And then if we go through all of them and all of them were equal to the root of the first index, then that means they are all in the same corrected component. So in that case, we can return true. Okay, and that's pretty much the core of the problem here. What's remaining is just to fill the function's definitions. Okay, so first let's define our union find. So union find, you need to keep track of the parents of each index of each node, and so the number of nodes we have is the number of indices, which is n, so we just do range of n. And this is what we need to find, n is just the length of the array. And how do we find? Well, basically find, we keep going up the parents sort of tree until we find an element who's equal to, whose parent is itself, because that's the root of, finds the root of the components that the element x is in. So, and the root doesn't have any parent because itself is the parent, itself is the root of the tree. And so we keep going until we find that element where the parent is of x is the same as x. Okay, and so how do we do that? Well, we just check if the parent of x is different than x, then that means x is not the root of this component that x is in. And so in that case, we want to go up and find the root. So we want to attach x to that parent. So we say the parent of x now, we need to find the parent of, the parent of x. And then once we find it, that's what we want to return it. So we want to return self.parent of x, because that's the root. Okay, so that's the find function definition. Now let's do our union function. So union, basically we want a and b to have the same root. So first let's check if they already have the same parent, So first let's check if we can use find, as I said. So we can check is the parent or call it root of a, root of b. If they are different, then that means we need to make them have the same root. Otherwise, we can just stop. But if they don't, that means we need them to be in the same components. So that means we need them both to have the same root or the same parent. And so to make them have the same parent, we can just take one of them and make it have the same parent as the other. So let's, for example, say let's have the parent of b have the same parent as the one for a. Okay. So we want one of them to have the same parent as the other, to be the parent of the other one. And so let's just do it like this. Okay. And that should be it for union find. Now let's implement our prime factors. So prime factors, let's divide it into even and odd. Do it in two ways. Find the even factors and the odd factors. The odd prime factors. Now for the even prime factors, there is the only possible one is 2. Because every other even number can be divided by 2. So the only prime shouldn't have any divisors. So the only prime even number is 2. And so we want to just check if 2 divides this, is a factor of this number a. So how do we do that? Well, we just check if it's divisible by 2. If a is divisible by 0, then we add 2 factors. We add 2. We need to define these factors here as a set. But the other thing is, we want to check here only the odds. So let's keep dividing by 2 until it's no longer divisible by 2. So, because, for example, 8, you can divide it by 2 once to get 4, and then another one to get 2. Right? So we want to divide, and then another one to get 1. So we want to keep dividing until we reach, until that it's no longer even. Now we look for the prime odd factors. How do we do that? Well, we only are looking for the prime odd factors, so we want to start from, we definitely want to start from 3. That's the first prime number, odd prime number. But we also want to add only 2, because if we add just 1, we will get an even number, and we know already that that won't be a prime factor. But when do we stop here? Well, we should stop at the square root. Why? Because if you have any number after the square root, then any factor after the square root, then you for sure have a factor before the square root. Okay, so that's why we do this. So we do math square root of a, and let's do int, convert it to init, and let's add 1 just in case we need to take the ceiling. And here we want to do the same thing, keep dividing by that number in case it's a multiple of it. And so, sorry, this is A, and then we divide A by I. And then we want to add I as a factor, so, okay. And then now after all of this, if the number is still bigger than 2, then that means the number itself is a prime factor. So, for example, for 5 or 11. For 5, it's not divisible by 2, so we'll go through this. It's not divisible by 3 either. It's not divisible, and we stop because square root of 5 is, so basically square root of 5 is 2.2. So we don't even get to 3. And so we will exit this without doing anything. We still have a 5. So that, but we still need to say that 5 is a prime factor of 5. So in that case, we check if the number is bigger than 2. That means the number itself is a prime factor. So we want to add it. A. Okay. Factors. Add A. Okay. And then at the end, we just return factors. And that's pretty much it, the implementation of the prime factors function. Okay, so now we filled up all the functions. We filled up our union find, we filled up our prime factors function, and we have the core of the algorithm here. So let's just run it. Invalid syntax. Let's see, this needs to be in. And we have n not defined. Let's see where. Yeah, if it's union find, and okay, this is here. We shouldn't pass in here, right? This is the class definition. We should do it like this, and then just pass it in the constructor. And that should be good. I think we are, yeah, this should be A. Sorry about that. And this is if the length, sorry, this is needs to be the prime groups of F, because that's what we are checking. And sorry, this also needs to be N, so let's just do N like this. And that should be it. Let's submit. And this gets accepted, okay? Yeah, so that's pretty much it. Now, this problem is also an application of union find, and the key idea is to see where the efficient part is, which is, in our case here, is the construction of the graph, and to try to find a better way to construct the graph. And here it happens also that we can actually construct the components without constructing the graph itself, and so that helps. Yeah, so that's pretty much it for this problem. I hope this was useful. Thanks for watching, and see you in the next one. Bye.